normalized in the table of normalized abundances. You can see the normalization effect also graphically under the sample abundances plot. One of my favorite plots I always look at when I do quantitation experiment and processing the data from it, because you see whether, first, you see whether the normalization improved the data. That's the first thing. It's important to see. And you also see whether the normalization caused some really massive changes. You don't want that, because if you have a problem with your sample, normalization will not fix it, because for the precursor based quantitation, for instance label free quantitation, if you a big change means that some of the samples must have been loaded in much smaller amount, which means that there are a lot of peptides might not be detected simply because they were below the level of detection, and not because they were absent in the sample which was loaded in lower amount. So always check. Remember, the scale is a log 10, so change by 1 unit is a 10-fold change in concentration, basically. To see it numerically and more exactly, you can look under the result summaries, quantification derived values, and there you will see applied normalization values listed for each of the sample. As you know, one of the samples will have value 1, that's the benchmarking most intense one, and then you see these normalization factors for the rest of your samples in that particular experiment. Question might arise, what fold change should I still accept for a reliable quantification? And the answer is it depends. It depends on the quantitation method. For instance, with the TMT type of quantitation, you would accept values up to about 2 or 3. So if you are strict, it will be 2. If you are a bit more lenient, up to factor 3 would be acceptable. For label-free quantitation, because we have more issues with missing values, the data are not so clean as with the TMT, I would perhaps say up to factor 5. But definitely be careful when it goes over. Those quantitations might not be reliable. So what about the other, yet another method of the normalization? Now I will showcase the method based on specific protein amount. And in that case, I again select the total amount as a normalization type. What is happening here? You need to provide the software with the FASTA file, which can contain one protein or multiple protein, depends. Those are your specific proteins on which the data will be normalized. What the software does, it identifies your peptides. It then goes and checks whether the peptide belongs to the normalization FASTA. If yes, it is included in the normalization, in this case colored blue, and you do it for all the peptides you detected. And then based on those which do belong or which can be mapped onto the normalization FASTA, those will be the ones which your normalization will be based on. And then numerically it is done in a very similar way. You add their contributions for each of the files. You select the most abundant one as a base and calculate the factors to use for multiplying relevant appropriate samples to bring all the samples to the same level. So this is the normalization on the specific protein amount, where you select a particular protein you want to use for normalization, and it could be one protein, it could be multiple proteins, it could be a whole species FASTA database if you have a mixed sample where such mixture of different proteomes is occurring. You can select one as a more or less proteins for normalization. Depends on the setup of your experiment in detail. So once again, highlighting the usefulness of not not only having option to normalize on total amount, whether it's the every all the peptides or just the specific ones belonging to a particular protein, you can opt for using the median. And I described the situation where a small set of proteins is drastically changing. That's where this should give you better result, more robust. A few words about scaling. Scaling is uh, having a very specific meaning for TMT type experiment, multi-batch TMT experiments. So we keep that aside. But in the precursor-based quantitation, the scaling is used to make your results, your quantitation values easier to look at. And you see it very nicely graphically on the snapshots here. Uh, while the abundances and normalized abundances are the numbers with this exponent in them, very difficult to perceive whether they are going up or down. The scaled abundances provide the benefit that they are more or less values we are able to interpret very easily. Uh, we have two types of scaling on all average and scaling on controls average. It's your choice which one you select. For a generic, label-free quantitation, most of the people will select on all average. So how is that then calculated? The calculation proceeds in this case by first taking the normalized abundance values and then calculating the average of all these values. This is then put as equal to 100, and all the individual normalized abundances are recalculated compared to that calculated average, what percentage they represent. So you will get values for proteins which are not changing or peptides which are not changing close to 100, yeah, 103 as you see, or 98, things like that. So, in my opinion, this could be a reason in favor of scaling, but in general, I think the scaling complicates the interpretation of the values, and things become a bit hairy when you have, mm, you know, sample groups with multiple samples and multiple sample groups. What the scaling is actually doing, because we are used to normally select a median of the samples to represent the group. But if you have engaged scaling, software indeed select a median. Looking at the green box here, I have sample experiment A versus B type. I have 3 replicas of each, control and sample, as you see here. And I would expect that the median value has been selected to represent the group of the 3 replicas. So value 86.8 for controls and value 122 for the samples, but not that's not the end of it, because the scaling steps in yet again and rescales those values yet again to the average of the two. So it just makes it a bit tricky to then find your way around. And I get practically every 2 weeks, 3 weeks, somebody telling me, how did PD came up with these values it shows in the abundances group? How is it possible? It should be just selecting median. Yes, it is, but it is doing yet another scaling. So I would, in a way, advise not to use scaling unless you have to for some reason, like in the TMT. It just makes things more difficult to trace. Okay. And now we are coming to a topic which is one of the bigger ones, protein ratio calculation. We have, protein abundance calculation. Protein abundance calculation. We have now 3 ways of calculating protein abundance. In the older version of PD, you were familiar with the summed abundances approach and top N average. version 3.3, PD 3.3, we are adding a sample replicate estimation. All this is somehow, you know, powered by the way to handle in some clever way the outliers, and missing values being the specific case of an outlier here. It's the summed abundances approach. Your protein abundance is calculated by adding the abundances of contributing peptides. Of course, if you have missing values in one of the files for some peptide, you don't get a quant value there. It could have a quite considerable impact on the final sum. That's why summed abundances is the method which is quite sensitive to missing values. That's why people sort of were trying to use some other simple methods like top and average. It is a bit more robust, but it is more or less a very non-selective outlier removal. And looking at the results I will be showing you later, perhaps you will not um, favor this method. At least I will not be anymore recommending it as more favorable than, for instance, the summed abundances. But luckily, we have the third new method, which is providing some smarter way of dealing with the outlier. But just to sum up, what is this new setting doing? It is calculating the protein abundance by estimating the most likely value, while it is looking at all the sample replicates. It performs automatically imputation, and that way it is handling the outliers and the missing values. It is um, you deployed in fragment and precursor ions quantifier, but it is not available in the report ions quantifier node. With this um, sample replicate estimation method for protein abundance calculation, we have introduced another related parameter, and I will you know, mention it here. It is called minimum number of peptide replicas for protein abundance. It is one of the advanced parameters, so you can only see it when you click to show advanced parameters. And what it does is it's one way of eliminating very unreliable results in case there are just too few peptides contributing to the quantification of the protein. And I will show you an example. Here it is. This is my protein of interest, this adaptin protein. It has been detected by 3 peptides shown in the middle of the slide. And as you see, if you look at abundances normalized columns in the second half of the slide, they are one of the peptides is an exemplary peptide, never missing a value, but the other two are a bit more troublesome. The result is that your CVs for the protein abundance are very high. These are the values which you probably wouldn't like, would filter that protein out. So there, what if we basically use the minimum number of peptide replicates as a filter to exclude contribution of unreliable peptides, peptides which do not occur in a minimum number of sample replicates. For instance, set it to number 2, which would eliminate the contribution of that last third peptide in the sample, in the second and the third sample group. We have introduced another colorful boxes column. Those are very popular. I know I get a lot of questions onto them. But in PD 3.3, we have yet another colorful boxes column called abundances grouped quant infos, which will tell you whether the peptides you are looking at are used or are discarded from contributing to the protein quantitation. So it's like a little traffic light system which should help you in evaluating the results. But let's have a look at what happens if I reprocess the data with the minimum number of peptide replicates set to 2. Then the suspicious peptide, number 3 here, drops out. Those values do not contribute, and that in itself has quite a powerful effect on the CV values for the final protein 1. So that is a very, powerful setting, powerful filter, and you should be aware of it. And once again, it's hiding under advanced parameters of the quantifier node. And now let's return back to the sample replicate estimation method for protein abundance calculation and see some comparisons. This sample replicate estimation, as I said, has been added as a smarter way to calculate protein abundance with a smarter way of handling the outliers and missing values. So what we would expect if we have a smarter way, that we should get in the end a better abundance CV values for the quantitation than with the original methods. And here, first snippet shows you the abundance CV values for summed abundance. It's very similar, perhaps just one tiny bit worse might be the CV values from the top 3 method. And then comes the sample replicate estimation method, which I would say absolutely fantastic improvement in the CV values. And I would like to guide you a little bit more through the steps which are happening in the background, how this sample replicate estimation works. We will be dealing with this example protein, which has four peptides contributing, and there are some missing values, and then there are also some outliers. So let's have a look in more detail at that. And the first question which arises when you try to deal with outliers is, how do you determine that something is an outlier? And for that, we opted for the method based on selecting the median CV value for a particular sample group and then multiplying it with a certain factor, in this case, factor 1.3. You can change it, but I would suggest you keep it. And then look into your particular protein of interest onto the contributing peptide values and decide whether the CV for a particular peptide is falling within that tolerance. So here, looking at the green abundances, you take that all the values in that box, ignoring the missing values there, and you select a median value. In my case, it is 30.6. Then, using the factor 1.3, you arrive to a value of around 40%, 39.8. You do the same for the sample group 2 and sample group 3, the red and the gray ones, and you get some values as well. And then you return to your particular peptide of interest, and you look at the abundances group CV values for group 1, for instance, the green one, and you see whether it is still within the tolerance you calculated. Remember, the tolerance for group 1 was about 40%. Our 88.9 definitely lies outside. And you go through all the values you have like that. And then the software steps in if you have selected sample replicate estimation and will replace the outlier, maximum 1 outlier per group, with something it will impute in there, and it will be the median of all values within the same sample group. Let's have a look at the example here in the middle on a group 2, where we have just one abundance value in there, highlighted in red, which lies outside the tolerance we stipulated. For the group 2, it was about 27.4%, and we see that this red value has 42% CV value. What will happen there? We select from these three values we have, as we have only three samples in this group, a median value, which is the value 3.97 e to the 4, and that one will be supplanted instead of the outlier. So in this way, we have replaced the outlier with the median value from that particular sample group for that particular peptide. And in that way, you continue with the rest of the outliers or missing values, and then you should hopefully see that the CV values get remarkably improved. If you look at it in statistical terms, remember we have the statistic insights notes. You can obtain the statistic very easily in Proteome Discoverer. Here is the three different sample groups. There was a different dilution series. That's not that important, but it just shows you that we have a particular values for CV in the top 3 method, and for the sample abundance method, you see those values are very similar, but they get improved if you use the SRE method, that means the sample replicate estimation method, even further improved if you sacrifice or exclude those peptides which do not appear in at least two sample replicates. Engaging that filter I have introduced a little bit earlier. So this is the overall impact, the impact of the new abundance calculation method on the CVs. What you see also graphically here at the bottom is the histogram of CV abundances, group CVs for the summed abundance method and the sample replicate estimation methods. And what you should see that there is a shift of the values towards basically proteins with lower CV. You see these plots here in, for different quantitation approaches, different abundance value calculation. And as I said, if you then on top of it engage this minimum number of peptides filter, you should get a further improvement. But of course, you will lose some of the peptides from, or you will exclude them from contributing to your quantitation. So that's working on top of that. Now, let me introduce a nice plot, as we are already talking about histograms and other tools in PD. This plot is a scatter plot, which you can build with abundance ratios, log2 values on the x-axis, and abundances grouped in this case on the y-axis. I like this plot because it is quite diagnostic. If you want to evaluate different approaches, you can plot your data in that way from your results very easily. You can color it by, in this case, the p-values. I believe this is colored. So what we will be using these plots for is for, validation or comparison of different methods. And what we look at is the shape. The shape should be as narrow as possible. So this Christmas tree shape should be as narrow as possible. The points should not be spreading too much. And the shape should be sort of straight. It should not be bending on the top towards the left or towards the right. And what we will be looking at is the number of outliers here, because this was an experiment which was a technical replica, different dilution series. We do not expect, in a way, outliers as such. All of the proteins should be twice as represent in the ratio 2 to 1. So let's see now how these plots look like for different quantitation methods. So in addition to looking at histograms, you can also look at this abundance ratio versus abundance plots, and you see strange things perhaps happening in the top three method, where there is a clear bias towards for high abundant proteins. Um, the summed abundances look okay, but that can be perhaps improved, as you see in this SRE minimum two peptide replicas. The whole width of the distribution is now narrower, smaller, so it is in a way a better method as well when you look at it in this graphical interpretation, not only the numbers in the